Oh, 10 minutes.
Thanks. You're right.
Up 6.
So
skip simple diffusion. Oh, okay.
It's there.
Diffusion. Okay.
So let's go ahead and talk about this for about another 10 minutes or so, and if we get all the way through, then we're cool, and if not, we'll finish it up on Thursday. So cell membranes. This is your phospholipid bilayer. This top little green, these green balls, that's that amino head, right? And these two little squiggly lines, those are your two your two fatty acid tails. And the bottom layer also has that green layer, but now it's pointed down because there's more water down here. And we have the phospholipids that are pointed up. And once again, these are the fatty acid tails, but we have tails from the bottom pointed at tails from the top. And what that means is that the water is only in contact with the surface where we have this charged surface, right? It's only in contact with the bottom where we have this charged surface, but it's not in contact with all of these guys in the middle because those guys don't get along with water. This is one of the reasons why if you take phospholipids and mix them with water, they will spontaneously form either micelles or these phospholipid bilayers.
What's the first one?
Micelles are just phospholipid monolayers, where the tails point in with no water on the inside.
Oh.
So, there is this spontaneous formation of this. And once again, the guy paying for that, because any reorganization of molecules has to be paid for, right? No, there's no such thing as a free lunch. Somebody's paying for it. Once again, the guy paying for all of that reorganization, the guy behind the curtain, entropy. Water doesn't like to hang out with these hydrophobic tails. And so the way to keep things comfortable is by organizing all the hydrophobic bits and having them hang out with each other. And pointing all the hydrophilic bits so that water can associate with them. What this means is that if you were to mix these phospholipids, not exceptionally simple, but relatively simple organic or pseudo-organic molecules that you can find evidence of in early Earth, you mix them together in an aqueous environment and you will get the natural formation of an exceptionally simplistic cell membrane, which by its very nature is semi-permeable, selectively permeable. Some things can get through on their own, which is how you get natural diffusion or passive transport. We mentioned this is why people who are hypoglycemic will sometimes take fructose tabs, because fructose can get through on its own. Glucose, the most common sugar in nature, cannot get through a phospholipid bilayer. At least not without help. In the form of one of these active transport molecules. Or actually for glucose, it's facilitated transport for a really stupid reason. Which we're not going to have. I might mention it, especially if you ask me next time, but we'll see what we get to.
Keep hating on entropy, and it sounds like the entire
He's not a nice guy.
It wouldn't, nothing would work.
But yet you are correct. We absolutely need him. It's like that uncle that you hate, but you don't tell him that because you're hoping he gives you a $100 birthday present. Well, we're still here, aren't we? So. Cell membranes consist of a phospholipid bilayer, a lipid bilayer, 2 rows of those phospholipids. They have the non-polar tails pointed down, the polar heads pointed out. We've already talked about all of this, but it is what defines, like when you think about it, what separates a cell from the environment? How do you know what is the cell and what is not the cell? It's the cell membrane. Now you might want to say a wall. Well, that works for this room because these walls are what separate this room from the rest of the building or the outside. But in cells, they don't have walls. Well, plants have walls. Yeah, sure, they have them outside of the cell membrane. It is the membrane that defines what is the cell and what is not the cell. It is the membrane that limits what can get in or out and what can't get in or out. It is literally the surface within which all of your cells interact with the environment. Whether it's the environment outside of us or the environment inside of us. Our internal environment that your cells have to respond to, get food from, exchange gases with, give waste to. All of that has to happen at the cell membrane. And it happens not just because of the phospholipid bilayer and the inherent semi or selectively permeable nature of it, but because we have over time evolved to have many, many, many other things in it, which is where we get this whole fluid mosaic model for the phospholipid bilayer of the cell membrane. It's the fluid, because here's the thing. When you think of that membrane, that phospholipid bilayer, that's a liquid. It is a fluid. It is easy to think of your cell membrane as some sort of a physical barrier, as almost like a plastic layer. It's just a layer of oils. It's liquid. It has to be liquid because we have to let things move around in it. We have to let things pass through it. It has to be liquid. But it is a liquid medium with liquid inside of it and liquid outside of it.
So all those transport channels, are those in suspension?
Yes. They're floating around in a soap bubble.
So they do migrate?
Yeah, they can move around.
Oh, okay.
They can move around, and therefore this is one of those things where we have things that are only stick on the outside, we have some that only stick on the inside, we have some that are channels that are outside and inside, we have some that are receptors that receive a message on the outside, don't allow it to go into the cell, but do change shape so that it releases something else on the inside, so the message that was received on the outside that never enters the cell can actually change something on the inside of the cell, but were it not for that receptor protein that was sitting in the membrane, the cell would have been oblivious to that message. It would never have known that it was there. We can talk about passive diffusion versus facilitated transport, which is just diffusion of something that would have done it anyway, except it couldn't get in the door, and so we gave it a cat door so it could get in. Or we could have active transport, where we're like, I don't know, grabbing cats and throwing them through the door. We're spending energy pumping something. That's active transport.
That's
Passive transport and diffusion are both free. Nothing is free, so who's paying for them? Entropy. Active transport, on the other hand, is where you're paying entropy to look the other way. Active transport is, I already got a lot, but I need more.
That active transport isn't the same as endocytosis, right? The proteins?
Endocytosis is a macro mechanism of active transport, yes.
Oh.
It is active transport that involves changing of the entire membrane as opposed to a change of the shape of one simple channel or carrier protein.
Okay.
But it's still actively spending energy to reorganize, to take in things, yes. You wouldn't call it active transport with respect to having an active transport carrier protein, but it is still you spending energy to concentrate a chemical, or more than one chemical. That bilayer is liquid. That is why we need cholesterol. It's why we need to be able to adjust the melting point of the fatty acids that we use in that bilayer, because we have to keep it liquid. If it turns into a solid, your cell's ability to interact with its environment goes away. Your phospholipids change their chemical makeup from winter to summer. Because when the average temperature your body is exposed to is cold, your phospholipids need to be longer in order so that their freezing point is also changed, so that they maintain the appropriate level of fluidity, so that things can cross in a controlled environment. Diffusion, facilitated, or active, going against a concentration gradient. One of the biggest active transports that all of your cells undertake is the active transport of hydrogen ions. There is a tiny little compartment in your mitochondria that is acidic as fudge. Because your mitochondria is spending a lot of energy pumping hydrogen ions into that tiny little pocket. In the same way that we spend a lot of energy building a dam and letting water collect behind it. And what can we do with water in a dam? We can let it roll down the gravity gradient to release a lot of energy that we can then capture. most of the energy that you get from burning sugars in your mitochondria is spent directly to pump hydrogen in active transport. And then a different protein will take those hydrogen ions and they will make ATP out of them. And here's an interesting factoid that you may or may not be aware of. That transport, that protein called ATP synthase, that's in us, it's in plants, it's in fungi, it's in the simplest of bacteria. Now granted, there are a few differences here and there in some of which amino acids come in what order, and we'll understand that later. But that molecule, ATP synthase, is in virtually every living organism on this planet. And it works in exactly the same way. We've just gotten better at feeding it. And we actually didn't. It was the bacteria that eventually became the mitochondria in our cells that did.
Last slide.
Last one?
Yeah. Last slide.
Because the rest are what? Oh, steady action, we don't care. Sure. Transport through cell membranes. It's just a summarization of the last two. These, except we've now added this. These two are free because entropy pays for it. These two are going down a concentration gradient. So it's already diffusion. It's the same. There's a lot on the outside and it wants to get on the inside. But if it can't get through the door, then we have to give it a door. Glucose is like that, except glucose needs a door that we activate, a channel that we allow to turn on, because we can turn it off. Insulin is one of the things that turns that channel on, so suddenly it's like, oh, right, so glucose can come in now, and when we don't have an insulin around, that channel is not functioning very well.
On the facilitated and the active, are those, you're just showing one, because are they bidirectional or?
It can go one direction or it can be bidirectional because it's actually facilitating in either direction, but we can force it by the addition of energy. And you can also have active transport that doesn't use energy in the form of ATP, it uses energy in the form of something else going down. So letting something else go down is the energy that we use to pull something else to go up, in the same way that you can do that pulley system for an elevator type of stuff, right? So there's all sorts of really complex mechanisms. It's that type of active transport that we use for our potassium and sodium concentrations. It's that active transport that allows our neurons to fire the way that they do, and then reset the way that they do, so that they can fire again the next time that we need them. Your cells are constantly controlling what does and does not get through your membranes. And it has everything to do with a soap bubble. A liquid soap bubble. This is why I somewhat oversimplification, I will admit, but why I say that you are just a trillion soap bubbles hanging off of a calcium phosphate skeleton. That does not diminish how important you might be as an individual, or how amazing you might be as an entity or biological existence. But that is literally what you are. A bunch of soap bubbles contemplating their own existence. Alright, we'll pick it up with 16 on Thursday.
On the quiz, did you mean to use L-fructose instead of D-fructose for the Hayward structure question? I would have gone the
Oh, I just used that because it was an image that I already had.
You dropped money on
So it'll still.
Yeah. It changes it's a different chiral molecule, but it's going to react in the same way, on the same Hayward structure. It's going to put one of those carbons.
Explain alcohols. What the difference is between
For this question? Okay. So, an alcohol is, or what is the functional group of an alcohol?
You'll have to just walk me through, I'm so tired.
So the functional group of an alcohol is a hydroxyl, the OH.
Yeah,
Right? Okay? So when you look at, when we talk about the solubility of hydrocarbons, we know that if it's just a hydrocarbon, solubility is 0. If it's just carbon and hydrogen, right? That doesn't go along with water at all. So by adding the hydroxyl, it creates a little bit of a dipole, right? That oxygen-hydrogen bond, just like in water. So it makes a hydrogen positive, it makes the water, it makes an oxygen negative. That makes it soluble in water if that water goodness is not overcome by too much CH2, CH3 badness, right?
Mm-hmm.
A hydroxyl is a little bit of goodness. It gives you a little bit of a dipole, just enough that it can associate with water and therefore be soluble, but only if you have 4 or less carbons. Past 4, because even at 4 you get partially insoluble. At 5 or more, it's not
Where
insoluble.
am I getting that it's partially soluble between, until 7, it's after 7, it's?
That is coming from carboxylic acids.
Okay.
Because you move from a hydrogen to, we talked about aldehydes and ketones. Well, that carbon-oxygen double bond creates an even stronger dipole, which means it's even more of a difference for water to hold on to. So now, instead of being soluble at 5, they're slightly soluble at 5 still,
then
but they have a
insoluble
problem at
at
6,
Yeah.
right? And then we get to carboxylic acids where we combine the double bonded oxygen and the hydroxyl at the same time. That shifts us up a little bit
So
more.
I just mixed the two.
Right.
Got it.
And so that's where that comes from, is that, and what it literally, it's just like, go back and look at the solubility of those different things, and it's right there on a table, and there's,
Yeah.
you know, yes or no.
Look at the mistake I made, because I didn't read the word accept. I was like, I gotta slow down and
You
read.
gotta be careful and answer the question that's asked, that is very true.
So, I'm curious, though, I'm still struggling with this, the Hayward structure.
Okay.
First of all, is there a Y? This hollow. Anyway, so, well, like I said, so this OH,
Right?
grabs this,
Mm-hmm.
and that's the ring. Aren't these two,
Those 2 carbons are not involved, yeah, on the outside.
okay, but when I look at the Hayward structure for fructose, whether it's D or L, it's always D equals.
It's the one that's usually drawn.
Oops. Oh, it's just,
Yeah, it's probably touch screens, yeah.
it's not modifiable, it's,
Okay.
so 1, 2, 3, 4, but this is shown as a penta, in everywhere I'm looking at it. But this would be, the correct answer would be 5, but I'm seeing 4.
Well, it's a penta ring because of the oxygen in the ring. There's only 4 carbons in it.
Okay. Okay.
It has the shape of a 5 point ring, but that's because one of those points is the oxygen.
Okay.
And the question is how many of the carbons are involved?
Oh.
4 of those.
That's the one on the quiz, isn't it?
Yeah, that's the homework, I think.
Yeah.
So the whole point of that, and the reason why I used it, is because that is like, do you understand what we're doing? It's not just draw the last carbon to the front, it's draw the last carbon, the last chiral carbon, to that double bonded oxygen. That's where the ring is. And everything outside of those is then either above or below the ring, but not in it.
Okay. Because everything I was looking at with fructose in Hayward structure, it still seems to be talking like one of these was still involved in the ring, and one of these was just hanging off. But
Yeah, but if you look up, like, do a Google for fructose.
Yeah.
It doesn't matter, it's already.
Oh, that's actually what that was. Just back up.
There you go. Look.
Uh-huh.
One CH2OH off the ring, and another one down here, CH2OH off the ring. 1, 2, 3, 4, and your 5th point's that oxygen. So, and that's the difference between a ketone sugar and or a keto sugar and an aldose sugar. The keto sugar is one down, and so on all of the other projections that you saw before, we have that one CH2OH heading past that last chiral carbon, right? Well, in a keto sugar, there's also one at the beginning of that line structure too, all the way at the top. But neither of them are in the ring when you form the Haworth projection, because the Haworth projection is always a reaction of the last chiral carbon with the carbonyl functional group on that carbon in the front. So that's
Carbonyl, not carboxylic.
well, the carbonyl is just the C-double-A-double-O. And so this is a carbonyl functional group because it's a C-double-O, but here it's an aldehyde because it's at the end, which means that there's nothing else hanging on, and we just have that one group hanging off the side, like in glucose. But in fructose, we have a keto sugar, and so we have two of them here.
There we go. Here's fructose. Okay. Ketose. 5 atoms. That's what screwed me up.
Yep.
Okay.
The oxygen is the 5th atom, but there's only 4 carbons.
And she's waiting. So
Yeah, I'll just say.
I just set up.
What's up?
What was this one here that told me that it was sealed? It's 5 companies. It's 5, one of them is peeling off. Which one is-
I have to show him this since he used to live down near there. My friend responded to an accident just a little while ago.
I think you have a very valid point, and I'm willing to bet that that's one of those where the second part of the question got cut off.
And actually killed him?
So send me an email
Well,
about
not quite, they
that.
had
Yeah,
to
because
finish.
I don't,
Yeah,
because a monosaccharide with 5 carbons, that tells you nothing. It could be all, it could be either.
Yeah.
That's the
It
second
could be
one
aldo
down
or
there.
keto, but it could, yeah, so it would be a pentose.
It'd be a bento.
Well, but they're
It's 5,
recalculating.
but it could be
Yeah.
either.
State, it should
You
have
don't
been.
know
There's that
where
and,
the last chiral is.
Yeah.
Yeah, cool. So
well, yeah,
email me about that one, and I'll
And
give you
then-
that point, and then I'll find it
not
in the question bank and make sure to correct it to make it more clear.
down around Brandon, so.
Oh, I thought it was up to Okay.
Is that right? Look, you've been to Cuba, haven't you, because you live in Raleigh?
I like, oh, Cuba, Missouri?
Yes.
Yes, yeah.
Friend of mine just went to